module, you will learn about the use of a transistor in the common emitter configuration as an amplifier. You have learnt that when a transistor is in the active state, a small increase in the base current IB causes a large corresponding increase in the collector current IC. Thus, a transistor in the active state behaves like an amplifier. The operating point of a transistor as an amplifier is fixed somewhere in the middle of the active region. We know that the current amplification factor, beta AC, is equal to beta DC. That is equal to delta IC by delta IB. Let this be equation 1. And the voltage gain AV is equal to delta VO by delta VI. Let this be equation 2. These expressions are applicable to the transistor as an amplifier of DC voltage. Now let us look at the transistor as an amplifier of AC voltage. An AC sinusoidal wave representing input voltage VI superimposes over the supply voltage VBB for the base emitter circuit. The input AC voltage VI causes sinusoidal variations in the base current IB. The sinusoidal variations in the base current IB introduce corresponding sinusoidal variations in the collector current IC. The sinusoidal variations in collector current IC produces corresponding changes in the output voltage VO, which can be measured across the battery VCC and the resistance RC. Large capacitors are used to block the DC voltages while measuring the AC variations across the input and output terminals. Let us now derive an expression for AC voltage gain in the transistor amplifier. Initially, let us assume the input voltage VI is equal to 0, and applying the Kirchhoff's law to the output part of the circuit, we get VCC is equal to VCE plus IC into RC. Let this be equation 3. Similarly, applying the Kirchhoff's law to the input part of the circuit, we get VBB is equal to VBE plus IB into RB. Let this be equation 4. When the input AC voltage VI is not 0, we get the sum of VI and VBB as VBE plus IB into RB plus delta IB into RB plus RI. Let this be equation 5, where Ri in equation 5 is the internal resistance of the input circuit, which is equal to delta VBE by delta IB. From equations 4 and 5, we can write the input voltage VI is equal to delta IB into RB plus RI. The input voltage VI can be written as VI is equal to delta IB into R. Let this be equation 6, where R is equal to RB plus RI. On rearranging equation 3 for the output circuit, we get VCE is equal to VCC minus IC into RC. Let this be equation 7. Thus, a small change in VCE, delta VCE is equal to delta VCC minus delta IC into RC. Let this be equation 8. Since VCC is fixed, delta VCC is equal to 0. Thus, a small change in VCE is given as minus delta IC into RC. The change in VCE is equal to output voltage VO. Then, VO is equal to minus delta IC into RC. Let this be equation 9. the AC voltage gain AV is the ratio of output voltage VO to the input voltage VI. Substituting the values of VI and VO from equations 6 and 9 in the equation for AC voltage gain, we get AV is equal to minus delta IC into RC by delta IB into R. Let this be equation 10. We know that the current amplification factor beta AC is equal to delta IC by delta IB. On substituting the current amplification factor in equation 10, we get the AC voltage gain AV is equal to minus beta AC into RC by R. Let this be equation 11. Then the AC power gain in a transistor amplifier is equal to the product of the current amplification factor and voltage gain. That is, AP is equal to beta AC into AV. Note that a transistor does not generate power. It just uses the power from the batteries in its input and output circuits to amplify an AC signal. You have now reached the end of this module. In this module, you have learned that a transistor is operated as an amplifier at the middle of its active region. The AC voltage gain in an NPN transistor amplifier in the common emitter configuration is given as AV is equal to minus beta AC into RC by R, where beta AC is the current gain which is equal to delta IC by delta IB. That is equal to IC by IB. RC is the resistance in the output circuit or load resistance, and R is the sum of input resistance, RB, and the internal resistance, RI, of the input circuit. The AC power gain in an NPN transistor amplifier in common emitter configuration is given by the product of the current amplification factor and the voltage gain. That is, AP is equal to beta AC into AV.